So, life in a post-quantum world. We figured we would wrap up today. Today's kind of more of our developer day. As you can see, we had a lot of security experts, hardware experts, blockchain expert, space, routing. Like, we wanted to bring a really well-rounded group of engineers and people that are all, rock stars in their own right, in their own field, to kind of could demonstrate some of the picture of how all of this stuff connects together, how this nexus, right, of things works. But the final thing that we're going to discuss is about a post-quantum world. So this is called Life in a Post-Quantum World, about quantum resistance, right? It's pretty self-explanatory. So let's start with the basics. Now, this presentation probably won't be too long unless I get monologuing. So we just expect 15 or 20 minutes, but if I keep going, and we'll open up to questions at the very end if there are any. I think we've got we'll see if I can get an inlet. I don't really have an input. I'm just on Zoom. But anyway, what is quantum computing? Very good question. A quantum computer uses quantum spin to encode layers of data through superposition. Now, that's a mouthful. What does that mean? Well, an electron or a photon, they have what's called quantum spin 1/2, okay? Quantum spin 2 means it's like a double-ended pencil. You spin something 180 degrees and you'll get the same side, right? It's a double-ended pencil, sharpened on both sides. So you get the same thing, the same effect on both sides. Quantum spin 1 is like a single-ended pencil. You spin it 360 degrees and then you get to the same side. Quantum spin 1/2, if you continue the math, means you spin it around 2 times before you get the same side. Well, that doesn't really make sense in a conventional space-time continuum, right? But what it basically means is that there's these different types of superimposed spins. The way that they say it is you have an up and then an up and then a down and a down, right? So you have 2 downs and 2 ups. So naturally, you make 1, a 1, 1, 1, 0, 0. So you have 4 possible states that this bit or qubit can be in, right? On this spin or on this spin, which means it can be a 0 or a 1 at the same time, right? And that's a really important distinction, which means that your computer is doing 2 things at the same time because it's superimposing itself over the space-time continuum. It's kind of like layers on top of one another, right? Each different spin and orbital pattern. So this means that this bit can be a 0 or 1 at the same time and create exponential computing capabilities, right? And that's why they're able to take some exponential algorithms and make them linear, or polynomial is the more correct name. Now, what does this mean for classical algorithms? Quantum computers are able to optimize classical algorithms that are normally unbreakable under classical architecture. So if you heard some of the people talk about some of the security aspects, right? Nothing really is secure. You're just resistant to attack at some point in the future. And generally that, resistance is on the order of billions of years. So it's computationally infeasible within any reasonable time frame for you to ever gain access to that system, because everything can ultimately be brute force, which means, you start guessing A, B, AC, AB, AE, and so on and so forth. That's brute forcing, right? And you're doing this linear attack. But that takes an incredible amount of time. So with a basic, algorithm, let's say a hashing algorithm, generally they have 256 bits of resistance, which means that it, 2 to the power of 256 cycles, which is, I think, 1.6 times 10 to the 77, right? 77 zeros, big, big, big number, right? Million has 6 zeros, okay? Billion has 9 zeros. Now, imagine 77 zeros, okay? So this is just a gigantic number. And that's where you get some of the foundations of security in classical algorithms, okay? Now, the 2 significant algorithms that are affected by a quantum computer are IFP and DLP. IFP stands for the integer factorization problem, which RSA relies on for security. RSA is probably one of the more widely used cryptographic primitives. Blockchain doesn't specifically use it because the keys are very big, but it is something that is used in most encryption systems, and it relies just on 2 prime numbers. It's P equals NQ. You have 2 prime numbers multiplied together, and you have a mathematical relationship between them, and the security of the algorithm comes in order to factor out all of the integers, in that large prime number, it just becomes computationally infeasible, right? So the next set of problems is called the DLP, discrete logarithmic problem, and that's what ECDSA relies on for security. ECDSA, I believe, is y squared equals ax cubed minus bx plus c. It's just an equation. It kind of looks like a little horseshoe if you drew an elliptic curve, and then you draw a line, right? And 2 points and 2 points are your private key and your public key, right? And there's a mathematical relationship, but the security comes in to resolve the discrete logarithm to find and derive that private key from the public key becomes computationally infeasible. Generally, it's about 1/2 of your bits. So, a 256-bit private key will have about 128 bits of brute force resistance from being able to crack that from the public key. And the security of these algorithms comes in the form that the public key, you should not be able to derive the private key from the public key. And if you can, it's considered insecure. Now, what does this mean for blockchain? Okay. Bitcoin and Ethereum rely on the discrete logarithmic problem for security. Bitcoin is protected using pay to public key hash only if a key is never used. Okay, so that means that if I just create a Bitcoin address and I receive coins to it and all of that, you're fine, right? A quantum computer cannot break that. But as soon as you make one transaction, only one, withdrawing those coins or any amount of those coins, you have to send it to a new key. Otherwise, you're vulnerable. But you also have another issue. Even if you only reuse the key once and then you try to switch your key again, you have a vulnerability window, which means that transaction is broadcast out over the network. Someone with a quantum computer could then take that public key, break it, and then push out another transaction. And since Bitcoin has replaced by fee now, I can just, crack that public key, re-sign it, put a higher fee on the re-signed transaction, and it's going to usurp all the other transactions in the mempool they're spending that same input, right? And that was a big issue that was created that reduced a lot of the security of zero confirmation transactions. So Bitcoin, even if you were really, 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 really careful with a quantum computer, you're still very vulnerable, right? Now, 1,792 qubits is essentially what a Bitcoin key would resist in a quantum computer. That's 1,792. Okay, that's nothing. I'm not sure the exact number, but I'm pretty sure it's in the trillions now of transistors inside your computer, like trillions, probably billions. I know I'm pulling this number out of my recto file, but I'm assuming it's anywhere on the orders of trillions of transistors. But even if we're looking at billions, the difference between 2,000 and a billion is significant, right? So what ends up happening now is this key can be broken in polynomial time rather than exponential time. So in the case, if we're using, I think it's the K-Zalka, no, the Pru-Zalka. Well, there's Shor's algorithm, and then there's the Pru-Zalka and the K-Zalka. One targets a binary curve, one targets a prime curve. I'm pretty sure it's the K-Zalka for breaking a prime curve. SECP, as you see here. P stands for prime, and then 256 is the number of bits, and then K stands for qubits. That's just a specific variation of the curve. It's just different equations and different also origin figures in that. So as I said, y squared equals ax cubed minus bx plus c, b, a, and c, and all those numbers, those have to be chosen carefully. And that's a lot of where the security comes in the key. And that's where some of the curves such as SECP256V1, which is the default curve used in OpenSSL, some people have postulated that it actually has a deliberately weak seed phrase that allows some form of deterministic lookup, right? Such as what Manfred was talking about, where people with paper wallets have just been making paper wallets open source. People assume since it's open source, it's safe, but they created a deterministic key generation algorithm in there that allows them to shorten or reduce the actual search space that they have to do to crack private keys. And thus, they have used paper wallet source code repositories to crack private keys without even a quantum computer, right? So the result of a quantum computer is it's like giving someone your private key when you give them your public key. Okay, because this number right here, 256 cubed, okay, is only 1.6 times 10 to the 7th, right? That's 1.6 million cycles to break a Bitcoin private key. 1.6 million cycles. So if we're talking about, conventional processors right now, I think mine's like 3 or 4 gigahertz. Okay, that's 3 or 4 billion cycles per second. Okay, so when we're talking about 1.6, if we have this really slow quantum computer that's like running 1 megahertz, okay, it would break a Bitcoin key in 1 second. 1 second. Yeah, it's really bad. Now, what it should be is 1.15 times 10 to the 77. Okay, so that's 77 figures. That's 77 numbers. So 70 more significant figures is how many are dropped off. Okay, it's an incredible drop in the security, and that's caused a lot of uncertainty in ECDSA and RSA. So when quantum computers reach 1,792 qubits, On Shorgo algorithm, the owner will be able to spend anyone's Bitcoin that reuses the address, just one, right? So that basically means it's as if your Bitcoins don't really belong to you if somebody has a quantum computer, because all they have to do is look for a private key or a public key. And that's with a quantum computer, that's just as good as having the private key. So pasting your public key, in a post-quantum world, if you're using ECSA, your public key, pasting your public key is synonymous to pasting your private key, right? So it's not going to be good when this happens, right? And 1,792 qubits is not far away. How developed are quantum computers? A quantum computer is like an ASIC right now. So that stands for application-specific integrated circuit, which means they are not programmable. Now, there is a language that Microsoft has created called Q, right? Q++ or Q# or something like that. And that's their attempt at starting to get people thinking about post-quantum algorithms. But the truth is that there's no universal quantum computer yet, okay? It's all ASICs, right? Just like computers were way back in the day. You need a universal quantum computer to program it because the universal processor has a wider range of instructions, okay, that you can send to it. And that's all a computer program is you're taking this human code and you're compiling that down into instructions to the CPU, okay? So the CPU needs to have a set of instructions that it can have, like move, compare and swap, a lot of floating point instructions are done in there. But, since there's no universal processors, there's no quantum memory, and there's also only quantum registers. Okay, so when you're doing, one reason that it requires 1,792 qubits is because you need at least 256 of those qubits to be a halting counter. That's a register that holds certain values while you're computing other values, right? There's no quantum disk, so they're a long ways from actually being on a consumer grade. Now, there's the Google D-Wave that some people have seen. They made a lot of, waves. Pardon the pun for that. And the D-Wave was really just a simple optimization algorithm. I mean, they barely have reached quantum supremacy, right? And so they're really only specialized computers that are only valuable at fulfilling a specific task. One of these is Shor's algorithm, which I discussed briefly a moment ago. And this Shor's algorithm essentially allows you to break any sort of ECDSA curve in, less than a second, pretty much. I mean, if you're running a 1.1 megahertz processor, 1.6 million cycles, that's nothing, right? So you're essentially in big trouble. Now, the other issue too is we heard a lot about nation state attacks, right? With Scott and his discussion, and that is a real threat. Nation states are threatened by cryptocurrency. Okay, so if you have the capability to build a computer that can break keys, would you? I don't know. Well, the NSA announced in 2014 that they're building a quantum computer to break keys. So since encryption's been under attack for a long time. They don't like encryption. They say exporting encryption devices is like exporting weapons. They don't want encryption to get out there. They don't want the public to have it. They've been creating deliberately weak private keys to try to allow the FBI to break. I mean, I think China has been making deals where they've got they'll allow encryption, but the CCP needs to have the master key and all of that stuff, right? So when it comes to disruptive technologies that rely on disruptive technologies like cryptography, which is a disruptive technology, you're a target. So you want to prepare for it. Are quantum computers usable? There's a lot of misconceptions about quantum computers. Right now, they're barely reaching quantum supremacy. That means that a quantum computer outperforms a classical computer in the same algorithm. I think from what I remember, there was only 1 or 2 algorithms that reached quantum supremacy. And the algorithms are not fully researched, so there's only a handful of uses currently. And the biggest issue and threat is quantum noise, which is kind of like white noise. Think of it as like white noise, but on the quantum spectrum, from the TV. When you have all that noise, that quantum noise, it's difficult to discern the actual wave form and the qubit. And that's why these are super, super, super cooled quantum computers. That's why they're close to absolute zero, right? Like, 5-10 degrees Kelvin. They're just really, really low temperatures because at a low temperature, you reduce the ambient background quantum noise and they need a quantum quiet channel in order to be triggering some of their observations, right? And essentially, what triggers a quantum state to change is you observe it, right? A quantum particle really acts like a wave until it's observed. And then once it's observed, then it becomes a particle. And look up the double slit experiment if you're curious about how that all works. And why that's important for this, because what's happening is you have this type of entanglement between these photons. And when you observe one here, it causes an adverse reaction over here. So when you're just doing a normal calculation, let's say 1 + 1 = 2 on a quantum computer, that could also be doing some other crazy mathematical equations as a byproduct, because you have all of these interrelations between these qubits. So it's not only can be a 0 or 1 at the same time, but it can also interact with another qubit in a quite type of superposition that will allows it to essentially do computation as a byproduct of computation, right? So we're just scratching the surface on quantum computers and what they're capable of. And that's why there's very few algorithms. I mean, there's not even been a fully function built quantum computer running Shor's algorithm yet, right? They're just theoretical quantum algorithms, knowing the logic gates and the quantum logic gates and how that works. And there's a lot of papers built on it. You know, the Shor's algorithm was the first algorithm that, you know, really brought to light everybody like quantum computers are going to destroy cryptography. And then there's variations of it, the K-Zalka, the Pru-Zalka, and those go into different specific implementations of ECDSA, you know, discrete logarithmic problem, right? So will it destroy Bitcoin mining? This is something I've seen a lot. And, you know, people say quantum computer, they're going to just mine Bitcoin. And they think quantum computer has more power than classical computer. And then they equate that with mining. And they think that's what's going to kill it. That really has very little to do with it, right? There's two main algorithms that affect cryptography in Bitcoin: the Grover's algorithm and Shor's algorithm. We've talked about Shor's algorithm. That destroys your public-private key pair security, okay? That basically means anyone can spend your Bitcoins, okay? That the security of your Bitcoins relies on that discrete logarithmic problem, okay? Where your address is a hash of your public key. And whenever you generate a transaction, you have to publish your public key to verify the signature does indeed come from that private key, okay? So there's no way around it. You have to reveal your public key at some point, okay? And based on Shor's algorithm, you know, 1.6 million cycles, poof, gone, right? Quantum computer has it. And since Bitcoin doesn't have any other security features in the memory pool, such as caching conflict resolutions, rejecting Fini attacks, creating conflicted blocks, and many, many other things, you're just a sitting duck. Once somebody gets your key, there's nothing you can really do about it. I mean, your transaction in the mempool already does not guarantee you that it's going to have finality, because they just do replace by fee. Which is basically, I just send the exact same transaction, but I increase the fee, which means I give more fee to the miner. And then that basically puts your transaction above the previous transaction in the mempool. So the previous one just never gets confirmed, and then yours goes through, right? So, you know, there's really not much you can do once a quantum computer comes out on Bitcoin. Now, Grover's algorithm can allow pre-image collisions on hashing functions with half of the required cycles a classical computer would use. Okay, so a 256-bit value, right? 256-bit hash has 128 bits of quantum resistance. Okay, so you basically reduce the bits in half. That's one reason why Nexus uses 512 bits standard for all transaction IDs. Okay, we use a 512-bit across the board. We only use 256 bits for less secure. We use 256 bits like 128 bits because we're designing Nexus to last for hundreds, you know, if not more years. So we needed to take into account of all of these, you know, issues that we have with quantum computers. And also, cryptography is not easy to change, especially in a mutable cryptographic system, right? You know, you can't just go to Bitcoin and be like, oh, hey, you know, we're going to upgrade SHA-256 and we want to make it SHA-512. It's not something that's easily done, even with a hard fork, because it's not retroactive, okay? Which means, you know, you could fix a key now, but that doesn't fix all the previous keys that have been published. So even your website, your security certificate, you know, I mean, if that's using a CSA or SHA-1 or any of that stuff, it's all vulnerable. And there's so many ancient platforms from the 90s, 2000s that just built and built and built and built and built, and they didn't think about these things. And now they rely heavily on these types of cryptographic primitives, and there's really not much they can do to upgrade it. Now, a little bit of context so that you guys can kind of start to quantify these numbers. 2 to the power of 123 is the largest number that is achievable to count to with a known energy in the universe. So that's why 128 bits is generally considered achievable security, because based on the known energy in the universe. Now, I didn't calculate this. This is just a figure that I found online, and it's been a pretty good quantification. the amount of electricity required to count that many numbers, just counting 0, 1, 2, 3, 4, 5, 6, 7, it not only would take you on the orders of billions of years, but it would also take on the orders of just more energy than we currently are aware of in the universe. 2 to the power of 256, okay, is more atoms in the known universe. Atoms. Okay, like the smallest indivisible atom means indivisible, right? The smallest unit that we're currently aware of. Okay, obviously it breaks up into protons and neutrons and quarks, so it is divisible, but I mean, kind of not divisible because you got the nucleus and all that, but we'll get to that later. But based on this, okay, Bitcoin mining will not be as affected as the keys themselves. I don't foresee there being a significant improvement in the Bitcoin mining because a quantum computer is still susceptible to cycles. It has a certain clock speed. It has to clock, and it can only go so fast, right? Grover's algorithm still is very, very misunderstood. It's not very well developed, and there's a huge quantum noise issue with Grover's algorithm. So, I mean, they've not really successfully done anything with Grover's algorithm yet, and they always have a classical computer error checking the quantum computer, right? So they're really still quite primitive, but the potential is there. And the biggest threat, I believe, is the loss of confidence, right? That's the nation state attack because, social engineering is so much more effective than actually attacking a system sometimes, right? Scaring people. Look at, all the things that are happening in the world today, right? Fear, 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 fear. So when you have a competing financial system that you don't want to compete with the dollar or, the petrodollar or the fiat currencies, you're going to try to take it out. And, we have a lot of, understanding of things that happened with Bitcoin that, have maybe driven it away from its founding roots. But, on the fundamental level, people want to save their wealth. They want a safe haven for their wealth, and they see Bitcoin as that. But when you have a quantum computer, is it that safe anymore? So how does Nexus address this? We developed numerous features to protect us against quantum computers. I first started researching quantum computers back in 2014. And that, originally, since there was no post-quantum cryptography back in 2014, other than some basic hashing functions like XMSS and stuff like that, I chose to just rely on Grover's algorithm to help hash the key and then to just increase our key size so that we could buy ourselves like a year or 2 years until they got to higher amount of qubits that would actually start to break it, right? So we, our original keys were about 3,800 qubits to break versus 1792. And the logic was at a point in the future, we'll get post-quantum cryptography matured enough where we can implement it in the network and we can protect ourselves with Grover's algorithm for the period of time. And we'll see the ramifications of quantum computers hitting the world. And the damage will be done to others before it will be capable of happening to us. And we also used 571R1 key. So it's over a binary curve. So it would require a completely different quantum computer in order to attack. So that was another method of protecting in 2014 is that, the quantum computers that they're developing are generally to break prime curves. So they would have to build a very special case to attack us. And it just wouldn't be viable, right? Binary curve. We're the only one that uses the binary curve, or we're the only one that uses the binary curve. But the first step, right, was reducing the attack surface of Grover's algorithm, which still retains exponential time. So we increased our hashing output to 512 bits for everything. And we actually do go to 1024 bits for our block hash or a proof hash, but that's not necessarily for the security aspect, but that was just for the prime numbers because our one of the algorithms that you can use to mine Nexus is searching for dense prime clusters. And I decided to get the number as large as possible. Kekic went to 1600 bits and Skyne went to 1024. So I figured, hey, you know what? I'll just go 1024 bits because that's that much bigger prime numbers. For a frame of reference, that's the difference between 1024 and 256. 256 is about 77 significant figures. 1024 bits is about 308 significant figures. So the second method we use is dedicated post-quantum algorithms that currently do not have vulnerabilities to quantum computers. That would be Falcon and Sabre. Falcon stands for Fast Fourier Lattice-Based Compact Signatures over NTRU. Okay, mouthful. But essentially what that means is it's, how do I say it? It's using the closest vector problem inside ideal lattices, actually specifically NTRU lattices, which are a very well understood mathematical construct. The cryptography around it is very well understood. And it's done with simple polynomial math. You don't have to deal with very, very large numbers like you generally do. You get the security on it by dimensions. Okay. So, you start with like a 2-dimensional lattice, and then you just have a bunch of points on there. And then let's say you want to find the closest vector to another point. And in a 2-dimensional lattice, that becomes difficult. But then when you make that a 10,000 dimensional lattice, okay, try to figure how that works. So, lattice-based cryptography is very compact for post-quantum cryptography, and it's also very, very fast. For a frame of reference, ECDSA, with elliptic curve digital signature algorithm, we support the brain pool 512T1 curve for our ECDSA variant, and we protect that through signature chains. I'll explain that in a minute. And then we also support Falcon's fast Fourier lattice-based complex signatures over NTRU. So ECDSA, the brain pool curve that we currently use, I think I maxed out with 8 cores. I got up to 4,000 signature verifications per second. So that was my maximum capacity. So if you're talking about UTXO architecture, I mean, you only can really process 4,000 inputs per second computationally. Okay, you have a computational bottleneck there. And unfortunately, with quantum tunneling, okay, which means that you have like this barrier and an electron here, and the electron should just kind of bounce off this barrier, but all of a sudden the electron decides to pop out of here and pop in over here. That's called quantum tunneling. Okay. And what ends up happening is you get a higher concentration, which starts flipping bits, and it starts breaking down the transistors, and ultimately it destroys your computer's computational capacity. So very important to protect against these quantum computers. Now, Saber is another type of algorithm that basically allows you to do encryption, right? Now, I missed a point. Falcon does about 160,000 signature verifications per second because it's only doing polynomial math compared to 4,000 for ECSA. So we have an incredible increase in scalability with Falcon, right? And we had to find some sort of better optimization on the computational bottleneck because processors aren't getting faster. We're at that saturation point where Moore's law for storage seems like it's still continuing, right? Moore's law grows exponentially, the blockchain grows linearly, right? That was part of Satoshi's vision of how Bitcoin scales, is that if the computing capacity increases exponentially, but the computing requirement only increases linearly, then you should always have ample capacity, which was true for a point. And it is a very, very sound, logical construct to make it work. But, for my studying of the source code and everything, you run into computational bottlenecks. And the only way that they've been able to scale processors out is to add more cores, as you guys have noticed, 4 core, 8 core, but they're never really getting over 3 or 4 gigahertz, right? Because you have saturation, the quartz crystal can only vibrate so fast, and, then quantum tunneling and all of these things. So we have this processing bottleneck that's forming more and more and more in these days, right? So we needed some way to increase the computational capacity. Now, you can do that through sharding, okay? But sharding is only one aspect of it because you want each shard to do as much as it possibly can. And so, if you're spending all of your cycles, let's say we're only doing 1,000 signature verifications per second, we're using 25% of our CPU. Now we've consumed 25% of our CPU. But let's say we're using Falcon and we're doing 1,000, right? I mean, we're at 1/16, like if not more than that, like probably a few percent of our CPU, right? Which, since it's very lightweight and it's very fast, you're using less resources, which will save you battery life. It saves devices. It doesn't wear down the device as much. A lot of software engineers these days have just said, oh, hey, since we have the computing capacity, why should we care about if it's 3 bytes or 4 bytes or whatever? Battery life, mobile devices, IoT, cube satellites, right? There's a whole other list of things too. And the other thing is, why make it do more work than you have to, right? Do you go walk around 5 times in a circle and then chant to the moon every time you go to the bathroom? No, you go to the bathroom because you need to go A to B, okay? But some coders that go, woo, okay, now I'm here, right? And that's what the computer's doing. And it's just, it's cumbersome and it's overcomplicated. And so, we focus on the simplest algorithms possible, right? So we authenticate with Falcon, which is an asymmetric cryptographic primitive, which means you have a public key and a private key. And the downside to Falcon, this is the only downside. I love it in every other way but this. It's about 792 bytes. That number might be a little bit off, so don't quote me directly on that, but around 700, 800 bytes for the 256-bit version of it. and I think about 900 bytes. I think it's about 1.5 kilobytes for the signature and the public key, compared to ECSA is 64, 120, 196, 192 bytes for ours because we use 512 bits. So you have, you have a lot more efficiency and processing capacity, but you're trading that off for adding load to the network and adding load to your processors, right? So right now we support both. Now, one way that we're able to provide this additional security, even if you choose not to use fully post-quantum algorithms such as Falcon, is through this conflict resolution system. So conflict resolution on Nexus basically means when I have a transaction and it's in a sig chain, okay, a sig chain, think of it as a mini blockchain. A conflict is one that comes in that's trying to occupy the same sequence number. It's very easy to detect. And UTXO is trying to spend the same input. So naturally what's going to happen when somebody, is trying to do a double spend attack, let's say they're trying to do a Finney attack, which requires 51% of the network at power, mind you, I would have one node on one side of the world and one node on another side of the world. And then I would be trying to buy something from a merchant here. I'd send them the transaction. And at the same time, I'd broadcast a conflicted transaction on the other side of the network. And, they would come across and then they would meet. And the way it works with Bitcoin is, some of it would reject and some of them wouldn't. And there's not really anything to understand what's happening, right? With us, we have this conflict resolution system, which essentially detects this conflicted transaction. So, the merchant would receive the transaction over here right at the same time that you produced this conflict. The conflict would propagate, right? And then eventually reach the merchant on the other side, indicating to the merchant that there was a conflict. So they could immediately designate that it could be a chargeback, a potential chargeback. So it gives the merchant extra abilities to protect. But also we have a hash, a next hash, and that's how you authenticate yourself into your sig chain, which is basically a hash of the next public key that can be used. And so we change a key every single transaction on Nexus, and then we hash that public key until it's used. And then as soon as it's used, then you rehash and create a new next hash, and then that's that. So, even with a quantum computer, you wouldn't be able to attack it because, for one, we have fully authenticated end-to-end encryption, okay? We're also authenticating it with a crypto object register. So I know without a shadow of a doubt that I'm talking to who I say that I'm talking to. And you can't do replay attacks because we timestamp all of that. So you have a secure communication channel. So even if somebody were to try to hijack it with a quantum computer, all they would be able to do is broadcast a conflict to the network. And when you receive a transaction that's conflicted, it's not going to relay to any of your peers, right? It's kind of like goes into a black hole. And if you produce a block with a conflicted transaction, that block goes into a black hole too. The only way that can get forced onto the chain is if another mining channel produces a block on top of that, right? You need to have this extra layer to build it and force that through. So it not only takes 51% of the hash power, it would take a quantum computer, and you'd have to break SSL too. You'd have to break TLS in order to succeed. And also Saber. Saber is what we're using for our end-to-end encryption, and that's a new post-quantum symmetric cipher, right? That allows you a key exchange protocol that allows you to generate through a post-quantum channel this symmetric key that allows you to do encryption. So we have many safeguards, and Falcon as well, which is something that we're going to eventually mandate. Right now, since quantum computers are still growing, and we have a lot of protections with contract revolution, the next hash, and all of these other things, we're fairly safe. And it's very easy. We made it so it's a retroactive system, which means all you have to do is click a button and you're upgraded. Okay. With Bitcoin, it's not retroactive, which means you could change one key or one address, but that's going to require everybody on the network to generate a transaction. And we all know how well Bitcoin tolerates that, right? Not very well. So what else can we do? Remember the satellites, right? There's a very new technology that's coming to life called quantum key distribution. This is something that I find really fascinating. Now, the Chinese have claimed to have done it through a laser beam, okay? But not sure if they have. The premise of it, though, is circulated around quantum entanglement, where you have two entangled photons, and you separate them, and you observe one photon, and the observation will trigger the same on the other, right? And so if you have these different observations to the different spins, 0, 1, 0, 1. But the interesting thing about this quantum entangled communication is you have no latency, zero latency, zero latency. You get that? That means it goes there and it's like instant. Okay. No matter if you're across the universe, across the world, right? And this is, I think, a key to, long distance communication systems, because to my understanding of it, quantum mechanics is kind of a window into higher dimensional understanding. It's outside of the space-time continuum. If we have the space-time continuum like this, it kind of like tunnels outside of it, and it can just drop back in any space-time coordinate it wants, right? So quantum key distribution is based off of this type of entangled photons. But the interesting part of it is matter and photons has an awareness of its observation or observer. Heisenberg, right, really brought this to light, where the uncertainty principle, hey, I observed something, and then the way I predicted observing causes it to change and become that which I observed. Like, wait, whoa, what's happening? Like, wait, do we have more influence over reality than we think? Maybe, right? So this entanglement relying on observation tells you if somebody else has observed. So if we've got, Joe and Alice, doing their little, and then Colin here decides to go, hey, what you guys talking about? This photon is going to shift. Let's just do it as a weird waveform like that. They're both going to go thumbs down, right? They're going to say, hey, man, like this Colin guy just like observed on our channel and he totally messed up our flow. Messed up as, like what's going on? Somebody's listening. So what you're taking advantage of with quantum key distribution is you're actually taking advantage of the ability for matter and subatomic particles and leptons, right? Leptons or electrons and photons, in order to allow them to demonstrate their awareness. So you have this space-time independent awareness of somebody eavesdropping on your specific channel, right? So this is really, really important, especially for long distance communication and new types of encryptions that also, protect against, instead of just having to use mathematics, we can use reality itself, because the photon knows when it's been observed. Because remember, it's all potential in a wave when it's not been observed. And once it's observed, it's crystallized based on that observer's awareness of it, okay? And that awareness changes its waveform, its shape, its quantum shape, right? Which that tells you, hey, wait, that's not Alice's observation. That's some other person. And so you can terminate the channel right then and there, right? So this isn't anything that would come very soon. It's kind of our, futuristic Star Trek. Yeah, this is where we're going to get. It's a very, very fascinating type of communication. I think that's going to take privacy to the next level, because you're essentially, tapping into the intelligence of matter. You're tapping into the intelligence of the space-time continuum of how these things, the awareness that they all have, and you're able to receive that awareness by observing that awareness in yourself, right? So that you don't have to worry about these man-in-the-middle attacks and have to physically watch. You just, the matter itself, the photons, just know, right? But wait, I thought aliens were bringing us a quantum financial system. I'm sorry, I had to say it. There's so much misinformation out there. I was like, quantum computing, I think I'm just going to drop this one in here. Okay, wait. Ever heard of social engineering? Well, yeah, LOLs. Yeah. Okay, let me just get something really quick. A quantum computer is not anything that's remotely practical to run a financial system on. That's number one. Number two, even if this were true and aliens were bringing us a new financial system, running on a single quantum computer would be the same thing over again, centralized, okay? So just because people say aliens are coming to do it does not mean it's going to be good. Like, this corruption is not exclusive to Earth, even if that was true, okay? A quantum-resistant financial system, though, is what is important, because all current financial systems will collapse when Shor's algorithm quantum computers reach 1792 qubits. Not just Bitcoin, Ripple, Bitcoin, Ethereum, JP Morgan Chase, can't remember the rest of them, Citibank, Bank of America, all these digital currencies, gone, right? So this PSYOPs is, I'm sorry, I'm making that's a bit of a judgment. I shouldn't say PSYOPs. This potential misinformation that is not grounded in reality or science, it seems like it's a part of the Great Reset agenda and whatever else like that. So just be careful out there. Verify things for yourself, okay? Don't read anything that is unverifiable, okay? Unverifiable. We need to make sure that we believe verifiable information, okay? The things that I've been telling you here are verifiable information. So quantum resistance is very important, okay? Quantum computing is very important in, the future of computing. Quantum resistant cryptography is very important for the future of security, okay? But the idea of a single quantum computer running this global financial system given to us by aliens, dude, Come on. I just had to address the misinformation. I figured while I was at it. So what will happen if the NSA realizes the quantum computer tomorrow? Well, we Nexus, we would be fine, right? We've known about quantum computing threats since 2014, been designing Nexus from the ground up to protect against them, right? Bitcoin users would most likely panic. The biggest threat is the loss of confidence in the system, and this would be very widespread, okay? That's what I think the biggest threat with quantum computers is the looming threat and the thought of people losing their Bitcoins and the loss of confidence in the system. That would be far more effective than trying to mine out all of Satoshi's old Bitcoins and stuff like that. It would reduce consumer confidence in the system. And, Bitcoin being a threat to the establishment, they could potentially do that, right? Ethereum contracts would empty faster than the DAO hack. DeFi liquidity pools would be drained. It would be a shit show. Okay. Now, here's the real big problem. Okay. It can't be fixed. They're already out. Okay. You can upgrade cryptographic primitives, but it's not retroactive. Okay. All the old keys from Bitcoin block 1, 2, 3, 4, 5, 6. Like what you just, hey, Satoshi, update your keys. Please move your Bitcoins. We need you. Oh, Satoshi's not moving his Bitcoins. Like, oh crap, there's 1 million Bitcoins. Wait, there's some vulnerable public keys. What do? You don't. That's the problem. I mean, there's not much you can do. It's not retroactive, right? You can't just make some new law and change it and then everything's just magically good. You have to build it from the ground up to protect against this, right? And so, some of the old Bitcoin transactions still use pay to public key, which was cool. The pay to public key hash is cool, but it changed, and some of the original ones were paid to public key hash, but some of the old coins from Satoshi's days are so vulnerable, or somebody that just reuses your Bitcoin address, like, hey, I'm gonna just receive. I do that sometimes. I'm lazy. I'm like, I don't want to create a new Bitcoin address. It's just and a lot of people will be that way too. So the only way to fix it, okay, would be for one, to produce new code that uses different key types, which seeing Bitcoin's upgrade process, I don't think that would go very fast. Number two, you've got to deploy that code and get everybody to agree and update it. Again, but Bitcoin's history, that would probably be very difficult to do. They've not successfully done a hard fork for God knows how long. I mean, it's been soft forks, right? Because people don't want to update their software. And number three, even with all of those things achieved, your Bitcoins still aren't secure. Like you update the wallet. Hey, I got the new Bitcoin quantum resistant. Yeah, your keys are so vulnerable because you have to generate a new transaction, which means you have to empty out all of your Bitcoins. Okay. Double check my new address. Okay, got to make sure I send it. Did it get there? Oh wait, send a test transaction first. Oh crap, I sent a test transaction. Wait, I used my key twice. Okay, I can't send a test. You see what I mean? It's going to be a shit show. Okay, to get people. Everyone would have to move the Bitcoins out of the old keys into the new keys. Since it's an immutable system, the keys are already there. The public keys are there. The hashes are there. The access is there. There's nothing you can do about it unless users actively move the Bitcoins. Now, let's look at Bitcoin's transaction capacity. It's kind of at a steady lull right now. Like the fees haven't been like ridiculous like they used to be, 5, 10, 15, 20, $30, when they get full. But still, you have, if you have every single Bitcoin address on the network, all of a sudden, try to move all their Bitcoins out into new post-quantum addresses, okay? It's just, the Bitcoin network won't even be able to support that very well, right? So, for Bitcoiners, if you're a Bitcoiner, start putting out a BIP or something like, BIP this. I know a lot of them are going to say, oh, they're not practiced so far away. It's like the Boost 2038 problem, right? Oh, it's so far away. For any of you that don't know, the 2038 problem is the real Y2K, okay? Y2K was a bunch of malarkey, okay? Unless some of those old COBOL systems actually didn't use a Unix timestamp, I'm sure something like that. Unix, right? The Unix timestamp is a number. If you've ever seen the Bitcoin timestamps, it's just this big, long number. It usually starts with like 1 and a 7, at least these days. It's this massive number. That's the number of seconds since January 1st, 1970. Now, currently, with a 32-bit timestamp, okay, 32 bits, 4 bytes, you can store about 4.3 billion entries in there. So that number is going to overflow. If you remember talking about overflows, it's going to go from 4.3 billion back to 0 because when you add 1 to the maximum value in 32 bits, it turns into zero again, right? It overflows back to zero. So you would have this overflow of the timestamp. Bitcoin currently uses 32-bit timestamps. It's not easily solved. Again, 32, so there's a lot of things that it's good to think about beforehand, such as, the number of bits in your timestamp, the types of keys that we use. And granted, when Bitcoin was founded, there really wasn't the threat of quantum computing, right? I'm not criticizing Satoshi. To be honest, Satoshi is, somebody I really look up to a lot. He's just the way he thinks, like, it just really taught me how to think this way too. I wouldn't be here if it wasn't for that man. So, I'm really grateful for what he did, but I'm also recognizing that Bitcoin's still kind of in its beta phases, and Satoshi never finished it. It was, a passion project of his to drive things forward. And when WikiLeaks started accepting it and stuff was when he kind of left. But there's a lot of anti-discussions to it because people don't want this to become a pressing issue in Bitcoin. And they think that, it's just going to be okay in the quantum computers and that's just conspiracy and whatever. But, it's all great until it's not. And that's the problem with these quantum computers is there's a lot at stake. There's a lot at stake. Okay. And there's not very many easily solvable solutions in the near term. I mean, even if Bitcoin releases software tomorrow, I'd give it a few years at least before you could say like a reasonable amount of the network was secure against quantum computers, right? It's a long haul. So if you're a Bitcoiner and you're concerned about this, just release a BIP or see if you can get them thinking about it. I've seen some people starting to think about it, and some people just label it as there are only 3 qubits, and no, you're way over exaggerating. It's like, no, they're a lot further along than you would think. And the NSA released publicly that they were building an algorithm to break cryptography in 2014. Okay, so that probably means they've been working on it for at least a decade, and they're getting pretty close. So I would give it about five years tops, maybe 10, right, before we start to see some negative effects from this, which will probably start quietly. Oh, hey, my Bitcoins are gone. What happened? And like little cases like that, little cases. And that's how it's going to start. And you won't really know it. And I mean, even if they do have a quantum computer, people wouldn't even know it's a quantum computer. They just see their Bitcoins are disappearing. And they're like, what? And then they're going to start talking about it. And then they're going to think it's a bug. And then they're going to be like, wait, it's not a bug. They actually have the private key. These are valid signatures. What's happening? Right. And by that time, it's too late. Right. So you want to make preparations beforehand. Right. As I said, it's not retroactive. So, if you upgrade your keys, your previous keys are still vulnerable. So the only way to ensure safety in a post-quantum world is to build it from the ground up, to protect it. Right. And that's what we've done. And, we've done that from learning from others and from learning from Bitcoin and learning from Satoshi and seeing how he thought and extending that forward. I mean, to me, Nexus is Bitcoin if Satoshi was able to finish it, right? I saw Satoshi's work and his vision and what he was doing, and I saw Bitcoin, and I saw it slowly diverging from that work. And that's one reason we started Nexus, is to finish that work, to realize that problem of a globally scalable, decentralized infrastructure, financial infrastructure that we can use for the next 100,000 years, right? Not 100,000, but 100 to 1,000 years. And one of those things, it's very important to make sure we take into account quantum computers, right? Because it is a looming threat, and it's only going to get worse as time goes on. So, if you're concerned about this, it's fine. There's lots of stuff out there. NIST has been doing a post-quantum competition. There's post-quantum cryptography getting standardized probably in the next few years. There's a lot of available algorithms. I mean, just start looking. It's really cool, and it's really interesting stuff. And it's really, really important. I've seen very, very few projects talking about that, right? It's very, very important. And it's just, it is. For the sustainability of a long-term system, we need to account for this issue. So after this garrulous speech, I will conclude it saying basically quantum computers, they're going to change the landscape of not just cybersecurity, but also blockchain security. The fixes to quantum resistance are not retroactive, okay, which means a fix now will not fix the past, okay, and blockchains are immutable systems. So even if you do move your keys out of old private keys, those old public keys can still get cracked. They're still there. They're still on the blockchain. You're just making them have 0 Bitcoin in them, right? That's it. But they're still going to get broken, right? So it's it's better to clean this up as soon as possible rather than, after the party. Watch out for viral videos that make unverifiable claims. Okay. Unverifiable. You can't verify that aliens are building a quantum financial system to bring us into this new whatever the fuck. Okay, pardon my language, but watch out for unverifiable information. If it's sensationalist, if it goes viral online, and if it's unverifiable, it's probably malicious. Okay, that's a general rule of thumb. Especially nowadays, if I see something go super viral, right, like expose CNN went super viral on Twitter the other day. Guess what happened? They removed the expose CNN Twitter viral hashtag. They tried to unviral it. Okay. Like anything that's going viral and still searchable, they want you to see. Okay. The things that they don't want you to see, censorship is so rampant, right? Just that's another good indicator too. If stuff's going viral, like be cautious of it. Okay. Be cautious of misinformation. And quantum key distribution holds promise for zero latency and quantum aware communication channels for a privacy focused high bandwidth future. And that is where the satellites are going. That's what I hope to get that in my lifetime, because that would be cool. So thank you everybody for tuning in.